Chapter 13, Inference about Correlation Coefficient. Correlation and the correlation coefficient have been discussed previously. This chapter looks at tests and confidence intervals regarding the correlation coefficient as well as regression coefficients. A test of the correlation coefficient is a test of the relationship between two continuous variables. The sample correlation coefficient is denoted by the lowercase letter r. The population correlation coefficient is denoted by the lowercase Greek letter rho. The null and the alternative hypotheses for the test of rho can be written as follows. The null is that rho is equal to 0 versus the alternative that it's not equal to 0. The test statistic for testing these hypotheses is as follows. It is assessed by the t-distribution with degrees of freedom n-2. That is slightly different from some of the previous tests where n-1 was the degrees of freedom. For example, is there a positive linear relationship between years of experience as a registered nurse and salary? A survey was conducted of 300 registered nurses, asking them their current salary and number of years of experience. Here in StatCrunch we have the salaries as well as the years of experience for the nurses. To test the hypothesis that the correlation is equal to 0, we would go to Stat, Summary Stats, Correlation, choose the two columns of data, go to Next, display two-sided p-value from significance test, and then calculate. What this gives us is the value of the correlation coefficient of the sample as well as the p-value in parentheses. Because the p-value is so small, it writes it out as being less than 0.0001. Now, this is a two-sided test, p-value, and if we're looking for just a positive correlation, then we would only want a one-sided test, p-value. To do that, all we would do is essentially double the value of our p-value, which would still give us a value that is smaller than 0.05. So the results of our test would be to reject the null hypothesis. We can clearly see that the sample correlation value is a positive correlation. The p-value associated with this test shows that it is a significant positive correlation. Had it been a negative value, it would have showed that it was a significant negative correlation. So if our test is to find positive correlation, and instead this is a negative value that is found to be significant, then that would not result in rejecting the null hypothesis. The two-tail test is actually a little bit more conservative than a one-tail test. So we are okay looking at the p-value resulting from the two-tail test, even though we are considering a one-tailed test for correlation, because StatCrunch isn't going to give us a one-tailed p-value. All it does is give a two-tailed p-value. Like I said, you can double the value of the p-value, and that would give you the p-value for a one-tailed test, and as long as the sample correlation is in the same direction, positive or negative, as what you are testing. Once again, we look at the difference between statistical significance and clinical significance. It is an important topic when dealing with the test of a correlation coefficient, because the null hypothesis claims that the population correlation is equal to 0. The value rho equals 0.01 is still not equal to 0, but does it show a substantial relationship, or does it show practical importance, in other words? Because it is such a small value, even though it is not exactly equal to 0, it still may not prompt any change in medical practice. So the educated reader of research literature should look at the value of the correlation coefficient and a scatter plot of the data to determine if there really is a meaningful association, regardless of whether there is statistical significance. Because statistical significance just means the correlation is not zero. But a correlation of 0.01, though it is not zero, still may not mean anything to practitioners and decision makers. We can also test for the significance of regression parameters. Recall that the equation for the population regression line is this. And this model has an unknown intercept and an unknown slope. The test for the intercept uses the following hypotheses. The intercept is equal to 0 versus the intercept is not equal to 0. The test for the slope uses the following hypotheses. The slope is equal to 0 versus the slope is not equal to 0. Both of these tests are conducted using t-tests and the t-distribution. However, the test of the intercept has limited value. All that the test for the intercept will tell us is whether or not the intercept of our regression line passes through the origin. If it doesn't, that may not mean anything to us. Even if it does, that may not mean anything to us. And so it's often not considered a test of interest. The test for the slope is the one that we are typically interested in. Let's look at an example of what statistical regression output looks like and what values it provides us with. Here is an example that comes from StatCrunch. We have y equals 17.26847 plus 0.8145621 times x. That is our regression equation that we came up with based on our data. So we have this value, which is our intercept estimate, and we have this value, which is our slope estimate. It tells us that the sample size is equal to 12. The correlation coefficient is 0.9595, and r squared, which is the correlation squared, is 0.92005586. The estimate of our standard error is 2.08. And then we have these two different tables of estimates and tests. So in this first row, in this top table, we have the intercept. We have the value of the estimate, which is the same as what it is here in the model. We have the standard error of that estimate, which is essentially the denominator of a test statistic if we're wanting to test whether or not the intercept is equal to 0. It would also be the value that we multiply by our table value if we are creating a confidence interval for the intercept. In testing that the intercept is not equal to 0, we have 10 degrees of freedom. We have a test statistic of 2.8673024 and a p-value of 0.0167. So if we're using a 95% test, this would tell us that the intercept is significantly different from 0, which again may not be very important information. Now we look at the slope. We have an estimate of 0.81, which agrees with what we have in our model statement right here. We have a standard error of 0.075666968, which again can be used to either test that the slope is equal to 0, or it can be used to create a confidence interval on the slope. In testing that the slope is not equal to 0, we have 10 degrees of freedom, and we have a test statistic of 10.76, which gives us a p-value of less than 0.0001, which indicates that the slope is significantly different from 0. This bottom table that we have here is additional information and additional tests. This first row right here indicates that it is about the model, or our regression model. This test right here at the end is an f-test to test the hypothesis that the slopes in the regression equation are equal to 0. So in fact, in this example, these two tests, the test of the slope and the test of the model, are exactly the same. In more complicated situations, you may have multiple slopes in a regression equation, and then this model test is testing all of them simultaneously, whereas this previous table would list out each of the individual slopes with each having its own test of significance. In a more in-depth course on regression, there would be more information discussed regarding this output here in this table. In summary, the test for the correlation coefficient tests the significance of the relationship between two variables. Statistical significance does not imply clinical significance. The parameter estimates for regression can also be tested to determine the significance of the slope and whether or not the regression line passes through the origin. That would be the test for the intercept, which again we mentioned may not be of interest. And that is the end of Chapter 13, Inference about correlation coefficient.